Hey everyone, it's Dr. Garner here. In this video, we're going to take a closer look at the different modes of radioactive decay that we introduced in the last video. The first mode of decay that we're going to examine is alpha decay. So as we saw, alpha decay involves the emission of a helium nucleus from an atom. And this causes the parent nucleus to lose 2 protons and 2 neutrons. So it's a helium-4 nucleus that's being emitted. It has a mass number of 4 since it contains 2 of each of these subatomic particles. We have an example problem here in which we're asked to predict the products of an alpha decay process involving uranium-238. So they ask us to write out the balanced nuclear reaction for the decay of this particular isotope. In approaching this problem, I would start by writing out the nuclear symbol for your parent nucleus. So in our case, we're starting out with uranium-238. So we're going to write in our symbol for uranium-238. For solving these problems, it's often useful to put in your atomic number as well. So if you look at the periodic table, you'll see that uranium is number 92 on the periodic table. So we'll write in its atomic number there of 92. All right, now on the other side of the reaction equation, we can go ahead and write in our alpha particle. So the nuclear symbol for our alpha particle would be helium with a mass number of 4. Again, the fact that it's 2 protons tells us that it's going to be helium, since helium is number 2 on the periodic table. All right, now we can figure out what the identity of our daughter nucleus would be, so the other product of this reaction, so we'll place that here. Again, we know that the sum of the mass numbers and the sum of the atomic numbers must be balanced on both sides of the reaction equation. So we can use that principle to figure out what the mass number of our other product would be. So in other words, whatever the mass number of the material here is, plus the mass number of our helium-4, is going to add up to give us 238. So in other words, whatever this is, plus 4 gives me 238. That means that the mass number of my product must therefore be 234. So 234 plus 4 adds up to 238. All right, the next step is to figure out my atomic number of my product. And the same principle applies here. Whatever the atomic number is that goes here, plus 2 needs to add up to 92. So that means that I need a 90 here to make that balanced out. Finally, the last step would just be to write in the symbol of whatever element this is. So for that, I would take my atomic number that I just found to be 90, and I would take that number and I would look at the periodic table and find the element that corresponds to the atomic number of 90. So if I do this, I should see that thorium with the symbol of Th corresponds to number 90 on the periodic table. So that's going to be the symbol that I'm going to write in for my daughter nucleus here. So the decay of uranium-238 via alpha decay results in thorium-234 as a product, as well as that alpha particle. Again, you can use the principle that the mass numbers and atomic numbers need to be balanced to predict what the products would be. All right, let's try out an example problem, a practice problem. As usual, I would suggest that you pause the video at this point and try this problem out on your own first. All right, in this problem, it's asking us which isotope would result from the alpha decay of americium-241. All right, so just like on that last problem, I would start out by writing your nuclear symbol for americium-241. And again, it's helpful to look at the periodic table and see what the atomic number of americium is. If you do this, you'll see that it has a mass number, an atomic number of 95. So I'll put in that atomic number here of 95. Just like we did before, we'll now write in our alpha particle. So it, again, is helium with a mass number of 4 and an atomic number of 2. Now I'll figure out what the mass number of my product should be. So again, whatever that is, plus 4 needs to add up to 241. So I can, of course, just subtract 4 from 241 to find that my mass number of my daughter nucleus is going to be 237. I need to do the same thing with the atomic number. So I need to take 95 and subtract 2 from it to give me my atomic number of 93 in my product. Now that I know the atomic number of the product, I can use that value and look at the periodic table and see which element corresponds to that particular atomic number. If I do that, I should see that element number 93 is neptunium. So it has a symbol of Np. So I can write that in here as my symbol for this particular element. At this point, I just need to compare this to the answer choices that I'm given. And it looks like neptunium-237, that corresponds to answer choice C. So that's going to be my answer for this problem. It turns out that this is actually a pretty relevant isotope, and many of you may have this particular isotope in your home and not even know it. So many smoke detectors of the type called ionization smoke detectors actually use a tiny amount of americium-241 in the detection of smoke. So that's actually how they work. So these smoke detectors, they contain this little ionization chamber that has a small amount of americium in it. And what happens is this americium, it emits alpha particles, and the alpha particles ionize the air that's inside of this ionization chamber. So the nitrogen and oxygen molecules in the air get ionized, and then there are these two plates that are charged due to the battery that's connected to them. And these charged plates either attract or repel the various ionized air molecules that are present in this ionization chamber. One side of the ionization chamber is closed off. This is used as a reference. And the charged particles in the air here, they of course move towards these plates and generate some amount of current that's detected by the smoke detector. And that's used as a reference. On the other side of the ionization chamber, we have particles that are exposed. All right, sorry for the slight pause in the video there. Just to resume, the other side of the ionization chamber is open to the air. So if there's smoke in the room, it can come into this ionization chamber and it can potentially react with the ionized air ions that are present in that chamber. And that will of course interfere with the flow of current between these two plates. And then that's sensed by the smoke detector and triggers the alarm that causes the smoke detector to sound. So it's actually kind of fun to think we have a small amount of this radioactive isotope in most of our homes. All right, so the next example that we're going to look at is that of beta decay. So as we saw in the last video, beta decay is a decay process in which a neutron becomes transformed into a proton and an electron. And that electron is known as a beta particle, and it's ejected from the nucleus at a high speed, so some amount of energy is carried along with it. And you'll see these beta particles written out using this lowercase Greek letter beta, or you might see it as a beta minus particle, indicating that it's an electron with a negative charge. All right, so we have an example here as well. So we have, we're being asked to write out the balanced reaction equation for the beta decay of cobalt-60. So just like we did in that last problem, I would start here by writing out my nuclear symbol for cobalt-60. So I would again fill in my atomic number as well. If I look at the periodic table, I'll see that cobalt has an atomic number of 27. All right, and then now that I have my parent nucleus, I would write in my products. So we know that one of the products is going to be a beta particle. So again, we can write that in terms of nuclear symbol notation using this abbreviation or symbol of E for electron, a mass number of 0, and an atomic number standing in here of -1. All right, so just like we did before, we can figure out the mass number of our daughter nucleus based on the fact that the mass numbers need to add up to be the same thing on both sides of the reaction equation. So whatever I have here plus 0 needs to add up to 60. So of course that's going to be 60. I can do the same thing with the atomic numbers as well. So whatever I have here plus a -1 needs to add up to 27. So of course that's going to be 28. And again, the last step is just to take this atomic number of 28 and look at the periodic table and see which element corresponds to number 28 on the periodic table. And you should see that that's nickel. And nickel's symbol is Ni, so I'll fill that in here as my last step. So this particular isotope is pretty relevant to medicine. Cobalt-60 is commonly used as a source of radiation for the treatment of cancer. So anyone who receives radiation therapy, cobalt-60 is typically the source of that radiation that's used to provide that therapy. All right, I want to take a closer look at positron emission as well. So positron emission, again, is a decay process in which a proton in a nucleus is transformed into a neutron and a positron. The positron, as we've seen, is often abbreviated with this beta plus, signifying that it's a positively charged electron. So it's a positron. It's the antimatter version of an electron. So it's like an electron, but with a positive charge. All right, in this example problem, we're being asked to write out the balanced nuclear reaction in which fluorine-18 undergoes positron emission. So again, we want to start by writing out our nuclear symbol, so fluorine-18. I want to fill in the atomic number as well. If I look at the periodic table, fluorine has an atomic number of 9. And now I want to put in my other product as well. So on the other side of the reaction equation, I'll write out the nuclear symbol for my positron. So again, we're going to use the symbol of E for electron, a mass number of 0, but this time since it's a positron, I'm going to use a +1 as my atomic number. Just like before, I'm going to use the fact that the mass numbers must be balanced to figure out what the mass number of my daughter isotope or product isotope would be. So whatever it is plus 0 needs to add up to 18. So of course that gives me 18 over here. Same thing with my atomic numbers. Whatever my atomic number is plus positive 1 needs to add up to 9. So if I do that, I get 8 as my atomic number. So 8 plus 1 gives me 9. Now the last step is just to fill in the identity of the element that would go here. So I would take my atomic number of 8 and look at the periodic table, and I would see that that corresponds to oxygen. So I would put in O for oxygen as my symbol here. It turns out that this particular isotope, fluorine-18, this is also pretty important for medicine as well. So fluorine-18 is commonly used in what's known as positron emission tomography, or PET imaging. So positron emission tomography is often used to diagnose diseases like cancer. So the way this is done is this radio-labeled fluorine, this fluorine-18 isotope, is added onto a glucose molecule. So normally glucose would have an OH here, where the fluorine is, but that OH has been replaced by this radioactive fluorine isotope. So this fluoroglucose, this version of glucose that has fluorine on it, is then given to patients that are suspected of having cancer. Cancer cells, it turns out, use a lot of energy, and they tend to use it in the form of glucose. So a significant amount of the glucose that you administer to the patient is going to find its way to these cancerous cells. Then once the radioactive fluorine is in those cancerous cells, it's going to undergo positron emission. So of course that's going to result in the emission of a positron. And as we've noted earlier, positrons are examples of antimatter. So antimatter is incompatible with regular matter. So when a positron encounters an electron, those two particles will annihilate. So they'll both cease to exist. Their mass will be annihilated and converted into energy. So the positron and electron go away, and out of that process we get out two gamma rays that move in opposite directions. Then a medical imaging device is used to sense those gamma rays, and using a computational method is able to reconstruct a 3D map of where each of these positron emissions took place within the patient. So this gives you a 3D map essentially of where the tumors are, where the cancer cells are within a patient. So this is a pretty powerful technique for diagnosing and detecting cancers. All right, so the next mode of emission that we're going to look at is gamma ray emission, or gamma radiation. So during gamma radiation, the nucleus transitions from a high energy state, or also known as an excited state, to a lower energy state. So it loses energy. So delta E is negative. Energy is lost during gamma radiation. This lost energy is released from the nucleus as a gamma ray photon. And again, you'll see this abbreviated using this lowercase Greek letter gamma. And as we've seen already, gamma rays are a region of the electromagnetic spectrum. So this is essentially a photon of light, a really high energy photon of light. The number of protons and neutrons in the atom don't necessarily change. So during just straight gamma emission, the number of protons and the number of protons and neutrons remain the same in the parent nucleus. So the identity and the mass number of the element do not change during gamma radiation. That said, all of these other modes of radioactive decay that we've introduced, such as alpha decay, beta decay, and positron emission, they also release gamma rays. So gamma rays can be released on their own or as part of another decay process like alpha decay or beta decay. One other property that's worth examining for gamma rays is that they're highly penetrating. So many of these other particles that we described, like alpha and beta particles, they're not particularly penetrating. They don't make it very far past matter. So a sheet of paper is enough to stop an alpha particle most of the time. But in contrast to that, gamma rays are very hard to stop. They're very hard to block and shield against. So that's why very dense materials like lead are often used for that purpose. All right, so on the last slide here of this video, I want to take a look at various units for measuring radiation. And we have a lot of different units for measuring radiation because you can measure radiation in different ways, depending on what it is you're interested in examining. The first mode of measurement that I'm going to look at here is the activity of a source. So what I mean by the activity of a source is how many radioactive decays take place within a material per unit time. So if you had some sample of a radioactive material, the activity of that sample would be the number of decays that take place in that sample per unit time. The SI unit for measuring the activity of a radioactive source is known as the becquerel. And this is defined as being one decay, so one radioactive decay, per second. And it turns out that's a really small unit of measuring activity. So a much more common unit is the curie. So curie is abbreviated CI, and it represents 3.7 times 10 to the 10 becquerel. So curie is a much, much, much bigger unit than the becquerel, and this is more often used in real-life scenarios. Another mode of, or another way to measure radiation would be in terms of the dose that's absorbed by a material. So in other words, how much radiation or how much energy is absorbed by a material as a result of exposure to a radioactive source. So this is the absorbed dose. The SI unit for absorbed dose is the gray, and it's defined as the absorption of 1 joule of energy via radiation by 1 kilogram of material. You also sometimes see this reported in units of rads, or radiation absorbed dose. So that's what rad represents. So 1 gray equals 100 rad. You can also think about the absorbed dose from the perspective of its effect on a biological organism. So this is known as the biological effective dose. So this is the biological impact, or the biological effect, of the absorption of a particular amount of radiation. So the units here are essentially the same, joules per kilogram, so the amount of energy absorbed from radiation per amount of material, presumably biological material, that's absorbing that radioactive dose. So the SI unit for measuring a biological effective dose is the sievert. And 1 sievert of radiation corresponds to approximately a 5% chance of developing a cancer as a result of that absorbed radiation. So again, this is from the perspective of the biological impact of absorbing that radiation. You'll also see the units REM used to measure this quantity as well. So 1 sievert equals 100 REM. All right, we'll stop there for this video. Thank you for watching.